Okay, so we want to continue our discussion of proofs by contradiction. And now we want to prove the following proposition, which is like a number theory proposition. Proposition 7.4, which says that there does not exist integers n for which 15 times m plus 35 times n equals 1. Okay, so that's our statement of number theory. And let's write this statement out in quantified form. So it says that there does not exist integers m and n such that this is the case. 15m plus 35n equals 1. Okay, if we send the not through, then P is equivalent to the statement for all m and n in the integers. 15m plus 35n does not equal 1, right? And that does make sense if you think about how that works. And so what's not P in this case, right? Well, it's easy to not the original statement because then the not's already pulled out front and the knots annihilate each other, so that we get there exists an m and an m in the integers such that 15m plus 35n equals 1. Okay, so that's what we're going to assume. And basically, we're assuming that there's a solution to an equation, and then we're going to derive a contradiction from that assumption, right? And so let's see how that works. So proof. Assume for sake of contradiction that there does exist an m and an n, which are integers, so that 15m plus 35n equals 1. So what we notice is that both 15 and 35 are divisible by 5. And so we're going to exploit that fact. So we want to just say, notice that 15m plus 35n is equal to, let me pull the 5 out, 3m plus 7n. And we know that 3m plus 7n is also an integer. This is actually one of the facts I showed you on the first day of class, that if you take integers and multiply them and add them together, you'll always get another integer. This says that integers are closed under addition and multiplication. You can't multiply them and add them and then suddenly get an rational number or an irrational number or a complex number or something like that. Okay, so now we're just going to divide by those sides by 5 and notice that we're going to get a contradiction. So dividing both sides of 15m plus 35n equals 1 by 5, we find. So we find this thing that we claimed is a integer is equal to 1/5. And Now this is a contradiction, right? Because the thing on the left is an integer, the thing on the right is clearly not an integer, and so this is a contradiction. So this is a contradiction since 3m plus 7n is an integer and 1/5 is not an integer. Hence, there is no solution in the integers to 15m plus 35n equals 1. Okay, great. So here's another example of a proof by contradiction, also a simple example, which is good, where we look at some number theory question. This is actually called the Diophantine equation, where you try to solve a polynomial in the integers. We show that it does not have a solution. And we notice that the form of a contradiction proof is always very similar, but the technique that we use to obtain the contradiction is very different depending on the setting. So now we've seen when we're working in the integers, a way of doing that, and we've seen with sets, but it really depends on the setting how we're going to find that contradiction. So there's a lot of ingenuity there in coming up with a creative way to obtain a contradiction. In the next couple examples, we're going to see more sophisticated versions of proof by contradiction.